Alright, so NASA just dropped a new update on this interstellar visitor. And honestly, this one's different. This isn't about some flashy new image or a cool tail getting longer. This is about the data itself, doing something it wasn't supposed to do, and when the data starts misbehaving, that's when things get interesting. Because it usually means one of two things is happening. Either the object we're tracking just fundamentally changed, or everything we thought we understood about it was wrong from the start. So let me walk you through what actually went down here. Because this is the kind of update that makes astronomers sit up straight and go, wait, what just happened? Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming. Next, every single day. Telescopes all over Earth and cameras mounted on spacecraft out in space are sending back measurements for this thing. They're tracking three main things. First, how bright it is. Second, exactly where it is in the sky at any given moment. And third, what its light is actually made of, which we call the spectrum. Up until now, those three measurements have been messy, sure, but they've at least been consistent with each other. They told the same basic story. Today, they didn't. Let's start with the brightness, because that's where this whole thing begins to unravel. For weeks now, astronomers have been working with what they call a light curve model. It's basically a mathematical formula that takes into account the comet's distance from the sun, its distance from Earth, how fast it's rotating, the angle we're viewing it from, all of that, and it spits out a prediction for how bright the thing should look at any given time. And the observations they've been getting have been bouncing around that prediction a little bit, which is totally normal. There's always some noise in the data, but they've been staying in the same general range, following the same trend. Then this newest batch of data came in, and the whole curve just jumped. Every single fresh measurement they got was sitting noticeably above where the old models said it should be. It's not like the comet suddenly exploded or flared up by a factor of 10 or anything dramatic like that, but it was enough that, when they plotted all the new points on a graph, the trend line just peeled away from the previous fit and refused to come back down. It's like the comet suddenly decided to act like a more reflective object, a more active object than the one everyone thought they'd been tracking this whole time. Now, on paper, you can fix that pretty easily. You just go into the model and change one number, this thing called the activity law, which basically tells you how strongly the comet's brightness depends on its distance from the sun. You tweak that number, and boom, the model fits the data again. But here's the problem. Once you start changing that number, it cascades into everything else. Because brightness isn't just some decorative property we're tracking for fun, brightness tells you something fundamental about what's happening on the comet. It tells you how much gas and dust is actively streaming off the surface. And that outgassing, that's not passive. That gas and dust flying off creates these tiny rocket pushes that actually change the comet's path through space. Which brings us to the second piece of this puzzle, the orbit itself. When NASA's tracking teams took all the new position measurements and dropped them into their orbital calculation software and asked the basic question, does yesterday's orbit solution still work? The answer came back as a very clear, no. Using the old parameters. Using the old estimates for how hard the outgassing was pushing the comet and in what direction. The predicted positions and the actual observed positions no longer matched up. The residuals, which is what we call the difference between prediction and reality, weren't just randomly scattered around zero, like you'd expect from measurement noise. They were biased. They were leaning consistently in a new direction. So, to fix that, they had to go back in and tweak what we call the non-gravitational acceleration terms. That's the part of the orbit calculation that accounts for the fact that this thing isn't just being pulled by gravity, it's also being pushed by its own outgassing. They had to adjust both the strength of that push and its orientation in space. And here's where it gets weird. The updated force that they needed to plug in to make the orbit fit the observations matches the new brightness curve, not the old one, the new one. In other words, the comet is not only brighter than the old model expected for its current distance from the sun, it's also being pushed harder and in a slightly different direction than it was before. And those two facts agree with each other. The data shifted together in a coordinated way. Now, that alone would already be enough to trigger an internal update in NASA's tracking system. But there's a third piece to this that really confirms something physical actually changed on the comet. The spectrum. The new spectral data, which is basically the breakdown of the comet's light separated out by wavelength so we can see what specific gases and types of dust are present. Doesn't look identical to what they were seeing last week. And I want to be clear here. This isn't some science fiction moment where a mysterious new line appeared in the spectrum that no one can explain. This isn't a radio signal buried in the noise. What actually shifted is much more subtle, but also much more telling. The balance. Certain emission lines from specific gases have become relatively stronger compared to the continuum, which is the baseline light coming from sunlight scattering off dust particles. At the same time, the way the dust is scattering light, especially at shorter wavelengths toward the blue end of the spectrum, looks slightly different than it did before, and that combination tells you something very specific. Both the gas production rate and the dust population have changed their character. Fresh dust is being launched, possibly finer particles than before, and slightly deeper or chemically different ESAs inside the comet are now contributing to the cloud of gas and dust surrounding it, what we call the coma. And that ties directly back into why the comet got brighter than the old model expected. It's not just reflecting more light, it's actually producing more material. So now, when you step back and look at the whole picture, you have three things that all changed. At the same time, you have a light curve that jumped onto a completely new track. You have an orbit fit that only works if you assume the outgassing force got stronger and rotated to a new direction. And you have a spectrum that confirms the gas and dust mix coming off the comet has physically shifted. That's what NASA means when they say the data shifted. It's not just that the measurements got noisier or that there's more scatter in the observations. It's that the relationships between the different datasets have fundamentally changed. So what does that actually mean is happening inside this comet? The simplest explanation, and the one that most comet scientists would probably lean toward right now, is that another layer of the nucleus just woke up. Think of the comet like an onion. It's built up of layers of ancient ice and dust that formed around a completely different star somewhere else in the galaxy, and then got ejected and spent billions of years frozen solid in the cold of deep space. When it came diving past our sun, the outer layers were the first ones to react to the heat. Those gave us all the early activity, the flares, the jets, the bizarre shapes in the coma that we've been tracking. But heat doesn't stop at the surface. It takes time, but it slowly migrates inward through the material, reaching deeper pockets of volatile ESAs at different times. Some ESAs sublimate, turning from solid to gas at higher temperatures. Some need to get colder to stay stable. When one of those deeper layers finally crosses its trigger temperature, when it gets just warm enough for those particular ESAs to start turning into gas, you get new vents opening up, new jets of material blasting out, new sizes of dust particles getting carried along, and new ratios of different gases mixing into the coma. And from the outside, from our telescopes here on Earth and in space, that looks exactly like what we just saw. The brightness curve jumps because there's suddenly more material being produced. The non-gravitational acceleration needs an update, because those new jets are pushing the comet in a slightly different way than the old ones were. And the spectrum quietly shifts because the chemical makeup of what's coming off the surface has changed. You don't see a massive explosion. You don't see some catastrophic event. You just see the whole dataset move all at once in a coordinated way. But there's also a less comfortable implication hiding in all of this. Every time the data shifts like this, every time a new layer wakes up and starts contributing to the outgassing, it means the internal stress distribution inside the nucleus has changed. New vents mean new forces acting on the material. New forces mean new torques being applied to the whole body. And new torques mean the spin state of the comet keeps getting adjusted, keeps getting perturbed. We've already seen hints that this comet is spinning faster than it used to be, and we've seen evidence that its rotation isn't clean. It's not spinning smoothly around one axis like a perfect top. It's more like a wobble, more like what we'd call a complex rotation state, where multiple axes are involved. If these deeper layers are now joining the party, if more and more of the interior is starting to outgas and contribute forces, that only increases the risk that all these small changes are going to add up to something bigger. More spin, angular momentum getting pumped into the system, more mechanical stress building up in the material, more chances for existing cracks to widen and link up with each other. At some point, the comet either finds a new stable configuration where all these forces balance out, or it doesn't. And if it doesn't, well, that's when you start talking about structural failure. That's when you start talking about breakup. Now, right now, NASA isn't putting the word breakup in the headline of this update. Officially, the language they're using is very measured, very technical. They're saying things like updated activity law, revised non-gravitational parameters, evolving compositional diagnostics, all of which are true and accurate descriptions of what they did to the model. But behind all that, technical language is something much simpler and much more stark. Their old model stopped working today. It just stopped fitting the data. They had to mark an update. They had to revise everything because the data shifted in a coordinated way, brightness, motion, and composition, all pointing to the same basic conclusion. This comet just ramped into a new phase of activity. Now, here's the key question. What happens next? If over the next few days or weeks, this new phase settles down, if the brightness starts following the new curve they've calculated, if the orbit solution stays stable with these new parameters, if the spectra stop drifting and lock into this new pattern, then this might just be one more step in the comet's long, strange journey out of our solar system. It'll be a chapter in the story, but not the ending. But if instead the data keeps shifting, if every new batch of measurements that comes in needs yet another model revision, if they have to keep tweaking the parameters every few days because nothing is settling down, then this marked update we just got isn't the story. It's just the beginning of a much more chaotic chapter. It's the first sign that this object is becoming fundamentally unpredictable. And that's what makes this particular update so significant. We're not just watching pretty pictures anymore. We're not just tracking a cool visitor from another star system. We're watching the numbers themselves refuse to sit still. We're watching our mathematical models of what this thing is and how it behaves fail to keep up with reality. Every time an astronomer has to open up their software and plug in new parameters because the old ones stopped working, that's not just a technical inconvenience. It's nature telling us that something physical changed on that object. And when those changes start happening faster and faster, when the time between updates starts shrinking, that's when you know you're approaching something critical. Right now, we're in this weird middle ground. The comet is clearly changing. The data proves that beyond any doubt, but we don't know yet if this is just normal evolution, just the expected progression as different layers of ice wake up and contribute to the activity, or if this is the beginning of something more dramatic. The thing about comets is that they're inherently unstable objects. They're not solid rocks. They're more like dirty snowballs held together partly by ice and partly by their own weak gravity. And when you heat them up, when you make the ice start turning into gas and streaming away into space, you're removing the very thing that's holding them together. You're undermining their structural integrity from the inside out. Some comets handle that process just fine. They lose mass, they get smaller, but they hold together. They make their paths around the sun and head back out into space in one piece, just a little lighter than they were before. Other comets don't handle it so well. The stress builds up faster than the material can accommodate. Cracks propagate, weak zones fail, and the whole thing comes apart. We've seen both outcomes play out with other comets in our own solar system. Some survive perihelion, approach to the sun, and some don't. And the tricky part is that it's really hard to predict ahead of time which category any given comet is going to fall into. Because we can't see inside them. We can't directly measure the internal structure, the distribution of ISAs, the location of weak zones. All we can do is watch what comes out, watch how the brightness and orbit and spectrum change, and try to infer what must be happening inside, based on what we see on the outside. And with this interstellar visitor, with something that formed in a completely different stellar environment under completely different conditions, we have even less intuition for what normal behavior should look like. We don't have a catalog of similar objects to compare it to. We're figuring this out as we go. That's what makes every one of these updates so valuable and so nerve-wracking at the same time. Each new data point, each new shift in the numbers, is teaching us something about what this object is made of and how it's responding to the sun's heat. But it's also bringing us closer to the moment when we'll find out if it's going to hold together or not. And the reality is, we won't know the answer until it happens. There's no magic threshold, no specific brightness or spin rate that tells you for certain that a comet is about to break apart. It's more like watching a dam develop cracks. Each crack by itself might be manageable, but you don't know which crack is going to be the one that links up with all the others and triggers a cascade failure. So, when NASA marks an update like this, when they say the data shifted and I had to revise the model, what they're really telling us is that we just learned something new about this object. And what we learned is that it's not behaving the way we thought it would. It surprised us. And in the world of tracking potentially unstable comets, surprises are rarely comforting. The other thing that's happening here, and this is more subtle, but equally important, that we're watching science happen in real time. Normally, when you read about astronomical discoveries, you're reading about them months or years after the fact, after all the data has been collected and analyzed and peer-reviewed and published. The uncertainty, the confusion, the false starts. In revised models, all of that happens behind the scenes and gets smoothed out before the public ever hears about it. But with something like this, with an active, changing object that's being tracked day by day, we're seeing all of that uncertainty play out in real time. We're seeing the models get updated because they stopped working. We're seeing the predictions fail and get revised. We're seeing scientists adapt their understanding as new information comes in. And that's actually a really valuable thing to witness, because it shows you what science actually looks like when it's being done, not just when it's being reported after the fact. Science isn't about having all the answers from the beginning. It's about building models, testing them against data, and being willing to revise them when the data tells you you got something wrong. The fact that NASA is marking these updates, the fact that they're publicly acknowledging when the model needs to be revised, that's not a sign of failure. That's a sign of the process, working exactly the way it's supposed to. They're following the data wherever it leads, even when it leads somewhere unexpected. So if you want to know whether this comet is going to settle into this new behavior, whether the updated model is going to hold, or whether we're going to see yet another shift in the coming days and weeks, well, we're all going to have to wait and watch together. The telescopes are going to keep tracking it. The data is going to keep coming in, and we're going to keep learning what this ancient visitor from another star system is really made of. And that's the story. Not just what's happening to the comet, but what's happening to our understanding of it. Every update, every revision, every time the numbers shift, we're getting a little bit closer to knowing what this thing truly is. We're watching the process of discovery unfold, one data point at a time. With all the uncertainty and surprise, and occasional confusion that real science always involves,